Well, we finally made it. This is Chapter 7 on integration, and so we're going to get into what's called the area problem today. Just as a reminder, as we go through this lesson together, it's best to have a place that's as quiet as possible. Try to make sure you don't have music going on in the background or any distractions. If at all possible, get into an area like that so that you can concentrate. All right, so let's go ahead and get right into the chapter. Well, traditionally, that portion of calculus concerned with finding tangent lines and rates of change is called differential calculus, and that portion concerned with finding areas is called integral calculus. However, we will see in this chapter that the two problems are so closely related that the distinction between differential and integral calculus is often hard to discern. In this chapter, we will begin with an overview of the problem of finding areas. We will discuss what the term area means, and we will outline two approaches to defining and calculating areas. Following this overview, we will discuss the fundamental theorem of calculus, which is the theorem that relates the problems of finding tangent lines and areas. And we will discuss techniques for calculating areas. Finally, we will use the ideas in this chapter to continue our study of rectilinear motion and re-examine the concept of a natural logarithm. In this introductory section, we will give an overview of the problem of defining and calculating areas of plane regions with curvilinear boundaries. All of the results in this section will be re-examined in more detail later in this chapter. So our purpose here is to introduce the fundamental concepts. The main goal of this chapter is to study the following major problem of calculus, 7.1.1, the area problem. Given a function f that is continuous and non-negative, on an interval, closed interval, a to b, find the area between the graph of f and the interval, a to b, on the x-axis. So we're looking for the area of this shaded region, as exact as we can get it, right here. Area formulas for basic geometric figures such as rectangles, polygons, and circles date back to the earliest records of mathematics. The first real advance beyond the elementary level of area computation was made by the Greek mathematician Archimedes, who devised an ingenious but cumbersome technique called the method of exhaustion for finding areas of regions bounded by parabolas, spirals, and various other curves. By the 17th century, several mathematicians had discovered how to obtain such areas more simply by calculating limits. However, the method of exhaustion and its successors lacked generality. For each different problem, one had to devise special procedures. The major breakthrough in obtaining a general method for calculating areas was made independently by Newton and Leibniz, both of whom discovered that areas could be obtained by reversing the process of differentiation. This discovery, which is regarded as the beginning of calculus, was circulated by Newton in 1669 and published in 1711 in a paper entitled De Analysis per Equationes Numero Terminorum Infinitas, or on the analysis by means of equations with infinitely many terms. And it was discovered by Leibniz around 1673 and stated in an unpublished manuscript dated November 11, 1675. Before one can talk logically about methods for calculating areas, it's necessary to have a precise definition of what the term area means. To avoid a lot of mathematical formality, let us assume that the areas of geometric figures with straight boundaries, such as rectangles, triangles, and polygons, are defined and computed using the standard formulas for such figures. However, the problem of defining and computing areas of figures with curvilinear boundaries is more complicated and will require various limiting processes. For example, in the introductory section of this text, we showed that the area of a circle could be viewed as a limit of areas of inscribed polygons. Thus, once a definition is established for the area of a polygon, the area of a circle can be defined as the limit of the areas of the polygons. There are two basic methods for finding the area of the region, having the form shown in the following figure, 7.1.1, the rectangle method and the antiderivative method. The idea behind the rectangle method is as follows. Take some closed interval and divide it into n's equal subintervals, and over each subinterval construct a rectangle that extends from the x-axis to any point on the curve, y equals fx, that is above the subinterval. The particular point does not matter. It can be above the center, above the an endpoint, or above any other point on the subinterval. In the figure 7.1.2, it's above the center. Here's a rectangle formed, here's a point sampled, and there's the value. So we would take the height of this rectangle, multiply it by its width, and that would give us an area approximation for this part of the subinterval right here. For each n, the total area of the rectangles can be viewed as an approximation to the exact area under the curve over the interval a to b. Moreover, it is evident intuitively that as n increases, these approximations will get better and better and will approach the exact area as a limit. Well, this process serves both as a mathematical definition and as a method of computation. We can define the area under y equals f of x over the interval from a to b as the limit of the areas of the approximating rectangles, and we can use the method itself to approximate this area. So here's an example where n is 1, 2, 3, 4, 5, n equals 5. And you can see that the rectangles are wider, and we can sample them, so we can add up the area of each rectangle, and that will be an approximation to the area underneath the curve. Now here, we let n equal 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And you can see that the rectangles are thinner, but if we add up all of the areas of each rectangle, it now becomes an even better approximation to the area under the curve. Here we let n be even larger than 10, and the smaller the rectangles get, the better the approximation gets for the area under the curve. And this is the limiting process. As n goes to infinity, the area, the approximate area, actually approaches the actual area under the curve. To illustrate this idea, we will use the rectangle method to approximate the area under the curve y equals x squared over the interval 0 to 1. We will begin by dividing the interval into n equal subintervals, from which it follows that each subinterval has a length of 1 over n. The endpoints of the subintervals occur at 0, 1/nth, 2/nths, 3/nths, and so on and so forth, up to n minus 1 over n, and finally 1. These are all the endpoints of the subintervals. We want to construct a rectangle over each of these intervals whose height is the value of the function f of x equals x squared at any point in the interval. To be specific, let us use the right-hand endpoints. So we're going to use the right hand of each subinterval, in which case the heights of our rectangles will be as follows: 1 over n squared, 2 over n squared, 3 over n squared, all the way up to 1 squared, which is 1. These are the right-hand sides of the intervals. And since each rectangle has a base of 1/nth, the total area, a sub n, of the n rectangles will be the sum of all the heights times the width. For example, if n was equal to 4, then the total area of the 4 approximating rectangles would be a sub 4, 1/4 squared, 2/4 squared, 3/4 squared, 1 squared, all times 1/4. 15 over 32, which is approximately 0.46875. Table 7.1.1 shows the results of evaluating the first equation here on a computer for some increasingly large values of n. So when n is 4, it's this. When n is 10, it's this. 100, this. 1,000, this. Notice it's getting closer and closer and closer to the actual area. The antiderivative method for finding areas reflects the genius of Newton and Leibniz. They suggested that to find the area under the curve from the very first picture that we saw, one should first consider the more general problem of finding the area, a sub x, under the curve from point A to an arbitrary point x in the interval from A to B. Figure 7.1.6. Newton and Leibniz discovered independently that the derivative of the function a sub x is easy to find, so that if one can figure out how to find a sub x from the derivative a prime of x, then the area under the curve from A to B can be obtained by substituting x equals b in the area formula a sub x. To illustrate how all of this works, let us begin with the problem of finding a prime of x is the limit as h goes to 0 of a of x plus h minus a of x all over h. That's the difference quotient. For simplicity, consider the case where h is greater than 0. The numerator on the right side of 2 is the difference of the two areas. The area between a and x plus h minus the area between a and x. If we let c be the midpoint between x and x plus h, then this difference of areas can be approximated by the area of the rectangle with base h and height f of c. Thus, a of x plus h minus a of x all over h can be approximated as f of c times h over h, which is just f of c. It seems plausible from the figure that the error in the approximation will approach 0 as h goes to 0. So here's x plus h, here's x, and so there's some point c between x and x plus h, so that you can plug in the value of c, get f of c, and that will be the area. As h goes to 0, if we accept this to be so, then it follows from 2 and 3 that a prime of x as the limit of h goes to 0 of the difference quotient is the limit as h goes to 0 of f of c. Since c is the midpoint between x and x plus h, it follows that as c goes to x, as h goes to 0, remember as h goes to 0, this interval gets scrunched together, so c is going towards x. But we have assumed f to be a continuous function, so f of c goes to f of x as c goes to x. Therefore, the limit as h goes to 0 of f of c is f of x, which means that the derivative of the area is a function f of x. This is the result we were looking for. It tells us that the derivative of the area function, a of x, is the function whose graph forms the upper boundary of the region. To illustrate how the antiderivative method works, let us apply it to the same problem we investigated with the rectangle method, finding the area under y equals x squared over the interval from 0 to 1. The upper boundary of the region of the graph of f of x equals x squared. So it follows from 5 that the derivative of the function a prime of x is equal to x squared. Thus, to find a of x, we must look for a function whose derivative is x squared. This is called an anti-differentiation problem, because we're trying to find a sub x by undoing a differentiation. By simply guessing, we can see that a sub x is equal to 1/3 x cubed, but that's only one solution. It's not the only one, since this follows from theorem 653 that a of x equals 1/3 x cubed plus c is also another solution. Remember, the derivative of a constant is 0, so therefore when we integrate this, or anti-differentiate this, we do so up to a constant. So 1/3 x cubed plus any constant can satisfy the equation a prime of x also equals x squared for any real value of c. We still have some work to do since this formula involves an unknown constant c that must be determined. This is where the decision to solve the area problem for a general right-hand endpoint helps. If we consider the case where x equals 0, then the interval 0 to x reduces to a single point. If we agree that the area above a single point should be taken as 0, then it follows on substituting x equals 0 in equation 7 that a sub 0 equals 0 plus c, which is 0, so the constant is 0. So equation 7 simplifies to simply a of x equals 1/3 x cubed, which is the formula for the area y equals x squared over the interval from 0 to x. For the area over the interval from 0 to 1, we set x equal to 1, which yields a of 1 equals 1/3 for the exact area under the curve. This confirms definitely which was suggested numerically in the table 7.1.1. Just a quick remark. Our success in finding the exact area under the curve y equals x squared was hinged on our ability to guess at a function a sub x whose derivative is x squared. We had not been able to find such a function. Then the antiderivative method would have failed, and we would have been forced to rely on the rectangle method. Thus, whereas earlier in this text we were concerned with the process of differentiation, we will now be concerned with the process of anti-differentiation. Okay, let's do problem 1 together. In exercises 1 through 4, use an appropriate formula from plane geometry to find the exact area between the graph of f and the given interval, and then use the rectangle method to make a table of approximations, a1, a2, all the way to a10, to the exact area, where a sub n is the approximation that results by dividing the interval into n subintervals and constructing a rectangle over each subinterval, whose height is the y-coordinate of the curve y equals f of x at the right-hand endpoint. So question 1, we've got f of x equals to x, and we're going to look at the closed interval from 0 to 1. And what we have here is our y-axis coming straight down like so, our x-axis, and our function y equals x. This is at 1, and this is at 0. Go ahead and dash that line down. Now, what I'm going to do is I'm going to break this up into n subintervals. And the way that that works is like so. Put 3 little dots for an ellipsis there. There we go. Now, we have to be able to label these points right here. Okay? Now the length of the interval, if I want to find the length of the interval, I'm going to take 1 minus 0, the right minus the left, and that's 1. So the total base of the triangle at the bottom is 1. Since I'm cutting it up into n rectangles, I take 1 divided by n, and that's the width of each of the rectangles, 1/n. So this first point right here is 1 over n. The second point here is 2 over n. The third point here is 3 over n, and it keeps following in this pattern, 4 over n, and then 5 over n, and it keeps going all the way up until I get to this point right here, which happens to be n minus 1 over n. And then when I finally get to this point, that's n over n, which is just 1. Now remember, what's the formula for the area of a rectangle? It's just base times height, right? And we're going to use the height of the function as the height of each of the rectangles. So what this is going to be what's called an over approximation. Let me show you why. Here's the first rectangle, the second rectangle, the third, and so on and so forth, to the fourth rectangle, the fifth rectangle, all the way out to the nth rectangle. Okay, so let's first consider a sub 1. A sub 1 means I only have one interval, so n is equal to 1, so it's the whole thing. It's from 0 to 1 is the base of the triangle. So the area formula, again, is going to be, I'm going to take the base times the height, okay, because I'm going to use the whole thing here as a rectangle. Let me go ahead and dash this out. This represents a sub 1, all this rectangle. So the base is 1, and the height is 1, which is 1. So a sub 1 is 1 times 1, which is 1. A sub 2 is if I cut this in half. So I cut 0 to 1 in half, and I use one rectangle here and another rectangle here. Okay. The width of this is equal to 1/2, and the width of this is equal to 1/2. The height here is 1/2, and the height here is 1. So this becomes 1/2 times 1/2, that's the first rectangle, plus 1/2 times 1, that's the second rectangle. That's 1/4, and this is 1/2, so 1/4 and 1/2 is equal to 3/4. So a sub 2, the area for 2 subintervals, is 3/4. All right. Let's now do a sub 3. So now we're going to cut this up into thirds. This is 1/3, 2/3. Bring this down. Okay, this is the first rectangle, the second rectangle, the third rectangle. Now it's clear to see that the width of each of the bases of the rectangles is 1/3. So all I have to do now is take each of the bases times their height. So I'm going to do it this way. A sub 3 is the first height, which is 1/3, plus the second height, which is 2/3, plus the last height, which is 1, all times 1/3, which is the base of each of the rectangles. Now this becomes 2 when you add up the inside of the parentheses, times 1/3, so it turns out that a sub 3 is 2/3. So we're getting even closer now. Now, how is it going to look like for a sub n? Well, the way that it's going to look like for a sub n is the first right-hand point is going to be 1/n. The next one is going to be 2/n, 3/n, all the way up to 1, times the width of each of the bases, which is 1/n. And so this is the formula for a sub n. Well, this becomes 1 over n squared plus 2 over n squared plus 3 over n squared, all the way up to 1 over n. And so that right there, even though it's not a real number right now, it's not an actual real number that we can see, that right there is the formula which represents the nth approximation to the area under the curve y equals x. So if I take the limit as n goes to infinity of a sub n, well, what's going to happen with that? Well, it turns out, and you can check with your calculator, let n go up to 1,000,000, and we're going to get 1/2. And there you go. That's number 1, all finished. God bless you, wherever you are today.
Praise Father, Son.
Praise Father.